Science Mission Directorate. I'd like to welcome you today to the media conference where we will discuss Kepler's mission and launch, now scheduled for March 5th at 10:48 p.m. at Cape Canaveral, Florida. Kepler is NASA's first mission that was capable of discovering Earth-sized and smaller planets in the habitable zones of stars much like our Sun. For those that are joining us in cyberspace, you can find out more information about this conference and more about Kepler itself by going to the website www.nasa.gov/Kepler. As for the order of events for this afternoon's conference, we have 4 panelists with us. Each will give a short 3 to 5 minute briefing, and then we'll open for questions and answers. Today's panelists include John Morris, NASA's Astrophysics Division Director at NASA headquarters here in Washington, D.C. William Bobricki, Kepler's Science Principal Investigator from NASA Ames in California. Next to him we have James Fanson, Kepler's Project Manager out of NASA JPL, also out of California, and Deborah Fisher, the Professor of Astronomy from San Francisco State University. And with that, I'd like to hand off the mic to John Morris. John?
Thank you, J.D. It's a pleasure to talk with you today about the Kepler mission. We're only 2 weeks from launch, and there's a lot of activities going on down at the Kennedy Space Center right now. As J.D. mentioned, Kepler is NASA's first mission capable of detecting Earth-sized planets around stars similar to our Sun. I call it our planetary census taker. True to NASA's pioneering spirit, Kepler will push back the boundaries of the unknown in our patch of the Milky Way galaxy, and its discoveries may fundamentally alter humanity's view of itself. Kepler is just the first in a series of upcoming missions that will greatly expand our discovery potential in astrophysics, and I'd like to show you the first graphic, which shows several of the upcoming missions. Kepler is on the left side of the graphic, launching the first week of March. Then we have Hubble towards the middle of the graphic with the servicing mission 4, currently scheduled for May 12th. Then we have the WISE mission scheduled for launch later in the year in November that will do an all-sky infrared survey to unprecedented depths. Then there's the New Star mission, a small explorer that will observe in the hard X-rays at active galaxies and black holes, due for launch in mid-2011. And then the James Webb Space Telescope, the successor to Hubble, now scheduled for launch in 2013. What's not shown there is also the ESA-led, European Space Agency-led missions Herschel and Planck, which are scheduled to launch in April of this year, and NASA is a partner on each of those missions. And then also our SOFIA Airborne Observatory, which will begin doing science later in this year. Now, the exoplanet exploration, which is the discovery and study of planets outside our own solar system, is a relatively new and quickly blossoming field in astrophysics. The first planet outside our solar system was confirmed only in 1995, and now there are over 300 exoplanets known. Most of these planets do not have Earth-like sizes or orbits. The Kepler mission is a critical component, therefore, in NASA's broader efforts in the areas of exoplanet research and astrobiology. Not only will its discoveries be profound on their own merits, but they will also significantly impact our future planning of missions. Kepler was selected through NASA's Discovery Program in December 2001. The Science Principal Investigator and the Science Office are at NASA Ames Research Center. NASA's Jet Propulsion Laboratory manages the mission through commissioning with the support of the Discovery Program Office at Marshall Space Flight Center. The main instrument and spacecraft were built by Ball Aerospace and Technologies of Boulder, Colorado. Mission operations will be done at the Laboratory for Atmospheric and Space Physics at the University of Colorado. And the data will be archived at the Space Telescope Science Institute in Baltimore, Maryland. The mission is named for Johannes Kepler, the German scientist who pioneered both the fields of optics and planetary motion. And now, 400 years later, we're using his discoveries in order to answer a profound and fundamental question about our place in the universe. Are there other Earth-like planets out there? And now, in order to tell you how Kepler is going to answer this question, is the science principal investigator, Bill Barucki.
Thank you, John. As John has mentioned, we know of over 300 planets around other stars currently. These planets are generally giant, gas giant planets, very much like Jupiter and Saturn, enormous gas balls. We're interested in planets like that of Earth, rocky planets in an orbit where life might be possible. Kepler is designed to find hundreds of Earth-sized planets, if such planets are common around stars, dozens of these planets if they're in a habitable zone. And if we find that many, it certainly will mean that life may well be common throughout our galaxy, because there's an opportunity for life to have a place to evolve. If, on the other hand, we don't find any, that will be another profound discovery. It will mean that Earth must be very rare. We may be the only extant life in our universe. In fact, it'll mean there'll be no Star Trek. We're hoping to find hundreds, of course, although Kepler will not find E.T., it's hoping to find E.T.'s home. The answers we get, whether we show there are lots of Earth-sized planets or very, very few, will actually answer a question that has been asked by mankind for millennia. In fact, since the time of the Greeks. They asked, are there other worlds, or are we alone? So we should get that answer. I've mentioned the habitable zone, and the habitable zone needs to be defined here. And so I'd like to start with the first animation. Basically, when we're trying to find these planets, we're measuring orbital periods. So if we have a star and the planet's orbiting about it in a very short period, that planet's going to be very, very hot. The super-Earth that was discovered earlier this month has an orbital period of about 21 hours and a surface temperature somewhere between 1,000 and 1,500 degrees centigrade. If that planet has oceans or lakes, they are oceans and lakes of molten lead. So not very conducive to life. On the other hand, if the planet we find has a very long orbital period, it's out a long distance from its star, it's going to be very cold. And in fact, we expect that it would be frozen, forever frozen, and again, we would not expect to see life evolve there either. So what we're interested in finding are planets that are not too hot, not too cold, but just right. We're looking for planets where the temperature is just about right for liquid water on the surface of the planet. That's the area we think might be conducive to life. The way the mission does this task, accomplishes this task, is to orbit a telescope, a large telescope that orbits the sun. And the telescope images over 100,000 stars on a set of CCD detectors. When we do that, what do I want to say? When we do that, what we're doing is something that you do yourself with your camcorders. Basically, you take images and you store those images and look at them later. This camcorder is really special. It has an aperture of about 1 meter. It has 95 million pixels, so it is a great camcorder. And the detectors, instead of being 1/4 inch, are square foot. So a very impressive system to allow us to look at this huge number of stars simultaneously. Now, when we look at these stars, we're not interested in the images. We're interested in the brightness of each of these stars. And could I have the next animation, please? So on the ground, we'll be getting these images, measuring the brightness of the star. And when a star goes across the planet, it blocks some light. The bigger the planet, the more light it blocks. So we get the size of the planet from the size of the dimming. We get the orbital period because this will repeat. If that repetition is a few weeks or a few months, it's obviously the planet's too hot. If we're talking about planets, stars like the sun, we're talking about repetition periods of about a year. We need, when we do this, to see about 3 transits. The first 2 transits tell us that of the orbital period. The third transit gives us the orbital period for a second time. The 2 numbers should agree to about a part